ReLU. Let us learn about ReLU activation function. In the last few lectures, we learned about sigmoid activation function and then about tanh activation function. What did we see? We saw that sigmoid is useful in many scenarios, but it was having certain drawbacks. Thereafter, we learned about tanh activation function. So tanh was able to cover up for some of the drawbacks of sigmoid, but still tanh was also having certain problems. If you remember from both these lectures, there was one major problem which was common to both sigmoid as well as tanh. What was the problem? This was a problem which was restricting initial layers of the neural network from learning fast, or sometimes it was restricting it from learning completely. So what was this problem? It was vanishing gradient problem. Automatically, the next thing you would think of is, or next thing you would want to know is, which is that activation function which can remove this vanishing gradient problem and still act as a useful activation function. So this is where ReLU comes in. So ReLU is the activation function which can remove vanishing gradient problem and still act as an effective activation function. Let us find out how ReLU is working, how it is removing this vanishing gradient problem, and how it is acting as an activation function. Okay. So first of all, what is an activation function? What is the requirement of it? You already know it introduces non-linearity in your neural network. So we'll see how is ReLU doing all these things. One thing to note here is ReLU is the most common activation function used. That is, let us say you are designing some CNN or any feed-forward neural network, you would generally be having ReLU as your go-to option or your default option. So let us start this lecture from there only. What is it that makes ReLU the default option? What is the reason that makes ReLU very acceptable in all neural networks? Okay. So the first thing you have to understand, like any other activation function, you should introduce non-linearity. So this is a must. Otherwise, it can't be an activation function. But there should be something that is specific to ReLU, right? First thing is, it is computationally simple. If you take sigmoid, for example, you have to compute 1 by 1 plus e power minus x. See, for the modern computers, this is not a very tough task. But comparatively, if you analyze, ReLU will become computationally much simpler. So we'll see what exactly is the formula for ReLU and how it is simpler. Okay. Next thing, this is the major point which differentiates ReLU from both sigmoid and tanh. And the point is, it does not suffer from vanishing gradient problem. So this is a very important point, especially when you're training a neural network. Okay. Now let us see what is ReLU, what is the formula, how it is not affecting the vanishing gradient situation and all. Okay. First thing is, this is the formula for ReLU. F of x, you will write it as, the value will be directly x as it is whenever x is greater than 0. That is, if x is greater than 0, you would directly take x itself. You are not applying any transformation. What if it is lesser than 0? In that case, you would directly write 0. This is what ReLU is. If x is less than or equal to 0, you would say it is directly 0. Another way of writing the same thing is, you can write maximum of 0 or x. Right? 0 and x, whichever is larger, that is what you will take. Either you can express it like this or you can express it like this. Both are one and the same. So at this point, you would be very clear of why it is computationally simple. You just have to see whether it's a value larger than 0, that is a positive value, or is it a negative value. If it is a negative value, you would simply put 0 as the final output. If it is a positive value, then whatever is the x, your input value, you are going to output it as it is. So this is why ReLU is a very simple function, right? Next thing is, let us draw the graph and understand how ReLU's graph will look like. If I draw the graph of ReLU, it will look something like this. Let us say this is my graph. I'll take a different color. I'll take blue in order to draw ReLU. Whenever it is less than 0, we said final output is also 0, which means at this point graph will be at 0, but at this point at x is equal to 0, from that point graph changes. Thereafter, whatever is the value of x, you are going to output as it is. So after this point, graph will look like the graph of y equal to x, right? Or f of x equal to x. So that graph will be something like this. This is how ReLU graph will look like. So this is ReLU. Okay. What did you understand? Till the point it hits 0, it is going to stay at 0 only. That is for all the negative values. As soon as it enters the positive region, what happens? Whatever is the value of x, the same value will be outputted by ReLU. So this is why it is a very simple function. The next question you will have in your mind is, why is this called as ReLU? Why is this rectified linear unit? That is, ReLU is a short form for rectified linear unit. Okay. Why is this called as rectified linear unit? Let us understand this, because understanding this will give you even more clarity about this ReLU concept. Okay. First thing, we'll see what is linear unit. Then we'll see what is getting rectified. Okay. Coming to the linear unit part, this function looks very similar to the graph of y is equal to x, or you can write as f of x equal to x. Both are one and the same. That is a graph at line at 45 degree. This will be y equal to x graph. What is the difference between the y equal to x graph, that is this yellow line, this is y equal to x, and the blue line is ReLU? What is the difference? The only difference is in the negative part, this tail is not present. Otherwise, it is same as this y equal to x line. What is linear here? This y equal to x line, this is a linear function. So for all the positive values, activation function is a linear function, y is equal to x. So you can say f of x equal to x. Because it is a linear function for all the positive values, that is where linear unit comes from. Okay. For now, just think that instead of this ReLU graph, you are having y equal to x graph. That is, this is the graph. In that case, you will call the complete thing as a linear unit, right? Because it is a linear graph. If it is the complete y equal to x graph like this, then you will call it just a linear unit. Next thing, let us see what is rectified. So this particular term rectified, it comes from the concept of signal processing. Coming to signal processing, rectification of a signal. What is rectification of a signal? Rectification means converting a signal such that all the negative values are removed, or need not necessarily be removed. It can be changed to positive as well. Either cases, you will call it as a rectified signal. For example, you have full wave rectifier in signal processing. What it does is, whichever are the negative values, these negative values will be turned into positive values. This is what you call as a full wave rectifier. Similarly, you have a half wave rectifier. What does it do? Whenever it has negative values, it will cut off those negative values. So either ways you can understand, rectifier in signal processing is useful for removing the negative side. So that is what you're going to do now. You have the y equal to x line, which is a linear line. This is the linear unit. Now we are going to rectify this linear unit. You are going to remove the negative side of linear unit. Then you get ReLU graph. This is what is rectified linear unit. Okay. So you rectified by removing the negative part of y equal to x line and converting all those into 0. This is how you made the linear unit rectified. Okay. So now you understood what is the concept of rectified linear unit. Next thing is, I already told you ReLU is very popular. ReLU covers up for the problems that sigmoid is having or tan H is having. Next thing we have to see is, what exactly are those problems? How is ReLU covering up for those problems? Once you understand this, your study about ReLU will be more complete. So let us see what are the problems that ReLU is solving compared to tanh and sigmoid. Okay. So the first thing we already discussed, that is vanishing gradient problem. Let us see where this is coming and how ReLU is rectifying. Okay. Vanishing gradient problem. Let us see how it is solving this vanishing gradient problem. First of all, what is this problem? Let us say you are having a feed forward neural network. You are training it. Then during back propagation, what happens? You will have gradients at each layer. So you are going to multiply gradients at each layer. So because your gradients are lesser than 1 in case of sigmoid and tanh, what did we learn? In sigmoid lecture, we had seen that all the gradients are lesser than or equal to 0.25. Similarly, in tanh also, it was lesser than 1. So in both the cases, if you multiply these values, then it is going to become smaller and smaller, which means by the time you reach the earlier layers, the value gets multiplied so many times that it will be as good as ignoring. It will be very close to 0. This is the problem of vanishing gradient. We saw sigmoid is suffering from this. Tanh is also suffering from this. So if ReLU should not suffer from this, what should mathematically be the situation? Think about this. If ReLU should not suffer from this problem, then gradient should not be lesser than 1. This is the first thing. Let us see how the gradient of ReLU is managed. Okay. So we'll see ReLU's equation here. Then we are going to differentiate and see the gradient. ReLU, we already know this is the equation. So if you take the gradient, because it is simple, I am directly going to write f dash of x. It is very simple because what is the gradient of x? You are going to differentiate x. You will get 1. That is x is differentiated with respect to x. That is d by dx of x. This will be 1. So your gradient is 1 whenever x is greater than 0. Whenever x is greater than 0, your gradient is 1. And what if your x is lesser than 0? In this case, your value of ReLU itself is 0, which means the gradient will also be 0. So whenever x is greater than 0, your ReLU gradient is 1. Whenever x is lesser than 0, ReLU gradient is 0. So looking at this itself, you know there are no values lesser than 1 whenever x is greater than 0. Now you can ask, okay, if x is lesser than 0, the value is 0 itself. So this is a problem. But what it is doing is, at least for 50% of cases, you don't have this issue at all. This is not a vanishing gradient problem, the 0, 1. Here you don't have gradient at all. So there is no question of vanishing. You don't have gradient at all at 0. Okay. So whenever x is greater than 0, you are having a gradient. Gradient is 1, which means at least in this case, you cannot hit vanishing gradient scenario. And one more thing to note here is, if you take the derivative at x equal to 0, actually gradient is undefined. For graph also you can understand, you can't differentiate at x equal to 0 because you have a bend there, x at x equal to 0. So actually it is undefined, but practically, let us say if you are implementing, you may say f dash of 0 equal to 0. So something like this you have to give so that for implementation it works. Okay. So what ReLU does with this gradient of 1 is, training in neural networks become much faster if you use ReLU. Why is it? Because your gradient is 1, so it will easily flow backwards in your neural network. Because it will easily flow backwards, your earlier layers get trained much faster compared to sigmoid or tanh. This is the scenario. So this is the first reason why ReLU is very popular. It is having advantage and everyone are using ReLU. Okay. What could be the second reason? This we already discussed in the starting of this lecture, that it is computationally simple. It is computationally efficient. So you know it is incredibly simple because max of 0x. This is a very simple computation. So computationally this becomes very simple. So again, this is useful for your training. One more point that can be made is, this point can turn out to be negative sometimes, but as of now, we are looking into the positive side of this point. That is, it introduces sparsity in your network. Sparsity means, let us say you are having a lot of, okay, I'm not erasing this. Let us say you are having lot of neurons in each layer. Then if you are using ReLU, what happens is for some of those gradient will be 0 or ReLU value itself will be 0. So when ReLU value itself is 0, those neurons you can consider they are not participating in this particular iteration, okay, or for this particular input they are not participating. They are kind of dead neurons because it is not giving any output. Output is 0. This another way of looking at is you are actually deactivating some of the neurons in your neural network, and effectively you are somehow preventing overfitting, because for different outputs in different iterations when you do this, some of the neurons may get activated, and for another output different set of neurons may get activated. Because of this, you will avoid the overfitting problem in your neural network. So this is the positive side of sparsity. In the coming lectures, when we reach there, we'll see what is the negative side of this. That is, if all your neurons go dead, that is also an issue, right? The whole neural network will become useless if you have a lot of neurons in order to learn a complex pattern. But then your ReLU kicks out all of them, then it all dies. Then kind of your neural network is useless. It will be like a one-layer neural network. So this is a problem with ReLU as well. For now, let us see the positive side of it. Okay. Next thing you have to understand is when should you use ReLU? This also we already gave a hint at the beginning of lecture itself that this is your go-to option, especially if you are having feed-forward neural networks, or let us say you are having CNNs. On all these cases, these days you are mainly using ReLU. Okay, so more than saying when to use, it may be better to say when not to use. That may be the better side. Okay, so you can say you should not use ReLU. You should not use ReLU whenever you suspect high rate of dead neurons. That is, we already discussed that the sparsity thing is there. That is, some of the neurons will be dead when you are using ReLU. If you are expecting that the rate of dead neurons will be high, then you should not be using ReLU. What is the reason? Because even if you have a lot of layers, lot of neurons in each layers, if most of them are going to die, then there is no point in having this whole network at all, right? So this is one scenario where you should not use ReLU. Another scenario we can think of is, let us say you have a lot of layers in your neural network, and then in the output you want a negative value. If this is the case, then at least in the output layer you should not use ReLU, because ReLU does not have the capability of outputting any negative values. It can output either a positive value or it can output 0. It cannot output a negative value, because of which if you are expecting, let us say, some negative output, at least in that case you should not be using ReLU. Before we conclude this lecture, let us just look at what are the negative sides or the disadvantages of ReLU. Okay, this is the last part of this lecture. So the disadvantage, first thing we can think about is unbounded output. From here itself you can see it. When we were using sigmoid or tanh, we had a bound for the output. That is, sigmoid was always outputting in the range 0 to 1. Tanh was always outputting in the range -1 to 1. So you had this bound. You knew that this particular neuron, after activation, it will output at max 1 and at least 0. Similarly, if it is tanh, you knew at least -1 and at max 1. But in case of ReLU, it will output the x as it is whenever x is greater than 0. So even if x is a very large value, it will still output the same value. So you don't have a bound for x. Whatever be the value, if it is in positive side, ReLU will print as it is. That is, the activation will put the output as it is. So there is no bound for ReLU. So unbounded activation is a problem, or you can say unbounded output is a problem. Another problem is, what do you remember the problem that we solved this with tanh? Initially with sigmoid we had a problem, and then we solved it using tanh. The problem was that sigmoid was not zero centered, that it was always outputting in the range 0 to 1. It was not a zero centered function. So we introduced tanh, which was a zero centered function. That is, from -1 to 1 was the range of tanh. Coming to ReLU, again this problem still occurs. That is, it is not zero centered. ReLU is having 0 and above are all the values of ReLU. So ReLU cannot be considered as a zero centered function. So this problem is also there. So that I'm not explaining because we already explained about this zero centered problem when we learned about tan H and sigmoid. And one more thing is the dying ReLU problem. So what happens is, okay, we'll take a dying ReLU in a separate lecture because we can explain more there. For now, let us say we'll conclude ReLU lecture here. You understood what is ReLU and what is its formula, how you can take the gradient, how it is getting off or getting out from the vanishing gradient problem, and why it is the most popular activation function right now. Okay, next lecture we'll see what exactly is the dying ReLU problem and how is that problem affecting our ReLU activation. Okay.